in person, but somehow we have to shift to this online mode. Maybe
I know.
some other time you will visit us. Yeah.
I was looking forward to come to Delhi.
Yeah.
Maybe the next time.
Maybe, yeah, some other time we'll invite you. Yeah.
Yeah.
How are things in Belgium, Carl?
Well, it's improving, but we still are in a lockdown. No restaurants, no pubs, no shopping.
Yeah.
Prof. Naukan?
Yes.
Okay. Yeah, we are actually broadcasting this one on IIT YouTube channel also, this evening lecture.
Oh.
So it will be directly broadcast to all student, faculty, and all alumni and all that. They can watch it. Yeah.
Right. Okay.
So I think we can start. So welcome to this evening lecture of today. So we have two evening lectures. One lecture will be given by Professor Claeys from Belgium, and the another lecture will be given by Professor Thomas from University of Buffalo. So I request Professor Naukant to chair this evening lecture. And Professor Naukant is very well known person to this electronic community in general and also in particular to physics people. And just to give a very brief introduction about Professor Naukant, he is presently the professor at ICEE Bangalore and chairperson of Center for Nanoscience and Engineering. And his research interest is nanoelectronic device physics and technology. And especially he has focused on sensors, gas sensors, biosensors, and he has developed very robust these sensors, biosensors, and he has received several prizes for his nice work. And one of the things I would like to mention that he got the Infosys award, and he is also the fellow of INE, and also the fellow of IEEE. So I request Professor Naukant to chair this session.
Thank you very much, Professor Neeraj Khare. It's a pleasure to chair this session. The first talk in this session is by Professor Claeys. I've known Professor Claeys for more than 2 decades now. It's indeed a great pleasure to introduce him. He is a professor at the KU Leuven, Belgium since 1990. He was with IMEC Belgium from 1984 till 2016. His main interests are semiconductor technology, device physics, low frequency noise phenomena, radiation effects, and defect engineering. He co-edited books on low temperature electronics, germanium-based technologies from materials to devices, wrote monographs on radiation effects in advanced semiconductor materials and devices, fundamental and technological aspects of extended defects in germanium, random telegraph signals in semiconductor devices, and metals in silicon and germanium-based technologies, their origin, characterization, control, and electrical impact. He co-authored 16 book chapters, over 1,100 conference presentations, and more than 1,300 technical papers. He is co-editor of 65 conference proceedings. Professor Claeys is a fellow of Electrochemical Society and IEEE. He was founder of IEEE Electron Devices Benelux chapter, chair of IEEE Benelux section, elected board of governor members, and EDS vice president for chapters and regions. He was also EDS president in 2008 and 2009, and division on the IEEE board of directors in 2012-13. He is a recipient of IEEE Third Millennium Medal and received the IEEE EDS Distinguished Service Award. Within the Electrochemical Society, he was chair of Electronics and Photonics Division. In 2004, he received the Electronics and Photonics Division Award. In 2016, he received China Special Recognition Award for outstanding involvement in the Chinese Semiconductor Technology International Conference. Today, the title of his talk is Materials and Device Challenges for silicon and 3.5 technologies for mobile application. Over to you, Professor Claeys.
Okay, good evening. It is a real pleasure for me to give this evening presentation. And what I would like to do is, because it's an evening presentation, I would like to give you a type of a guided tour through the wonderful world of material and device challenges in the field of silicon, germanium, and 3.5 technologies. We all know that nowadays the application is driving the evolution in the technology. And if you look at the last 5-6 decades, we can see on this view graph that starting in the 70s, aerospace was dominating the need for microelectronics, and we only needed a few thousand components. Then we switched over to mainframe computers, PC, then to mobile communication, and there we already needed more than 1.8 billion units. More recent, we were entering the world of smart computing, and today we are dealing with Internet of Things. And there we need more than 100 billion units. It's a huge amount of activity required in the world of microelectronics. That means we need massive convergence of data processing, storage, and bandwidth. And if you compare 4G with 5G, we need about 100 times more data rate, 1,000 times larger bandwidth, and a smaller than 1 millisecond latency. Now, if we speak about Internet of Things, 5G is dominating the total field. And in general, 5G applications can be divided into 3 main domains. The first one is a domain of enhanced mobile broadbands, where we have mobile devices, tactile internet, streaming, that type of applications. The second domain is called mission critical services, where we are speaking about automotives, robotics, healthcare application, smart grid, and so on. And then the third very important field, we call that massive Internet of Things, a huge amount of different type of applications, all relying on Internet of Things, where we want to combine, to connect people with people, but also things with things. And for each of the 3 different domains, the specifications are quite different. For instance, for mission control applications, we need strong security, we need ultra-high reliability, ultra-low latency, and extreme user mobility. If we think about the normal massive Internet of Things, there we need ultra-low density, ultra-low complexity, very important ultra-low energy, battery lifetime is extremely important and will dominate whether or not there is a breakthrough in a particular field. And of course, we need deep coverage. We need to be able to interact at very, very remote areas, interacting with people, interacting with things. And then the third field is enhanced mobile broadband, where we need extreme capacity, extreme data rates, and deep awareness. And all areas of the industry will be impacted by Internet of Things. That means we will see an impact on the entertainment, on smart driving, on healthcare, agriculture, smart cities, and so on. So every domain will be impacted. And thanks to 5G, we have the creation of new values and a redefinition of the industries. The evolution of microelectronics, we can compare that with the evolution of the human mankind. And I'm not going to explain Darwin theory, that would give a lot of discussions, but we see in the evolution of the human beings, where originally we were pleased with a banana, nowadays we need a smart device. And we can only have the smart device thanks to the strong evolution in microelectronics, where the first transistor was fabricated in 1947. Then we had the first IC, the first monolithic IC, and only 60 years after the invention of the transistor, we had already 3 nanometer nanowires. So very strong evolution, enabling all the nice applications that we are using in our everyday life. If we are speaking about bringing to the market a new technology, there are 3 phases. We have a research phase, we have a development phase, and then of course we have a production phase. And today, in 2020, we are already dealing with sub-10 nanometer technologies. You can buy sub-10 nanometer commercial devices. And to give you a feeling of the evolution, here is a very recent graph from ICEE Insights, which is giving the installed monthly capacity versus the different type of technologies that have been used. And if you look at the bottom one, the blue area, there we see that at the end of last year, about 4.5% of the installed capacity was dealing with technology smaller than 10 nanometers. And within 5 years, by the end of 2024, we are going to see a share of about 30%. Of course, we can only do that by relying on scaling. And scaling, we all know Moore's law. But there are different ways in which you can do the scaling. The first standard, straightforward way of scaling is called geometrical scaling. That means you're following the well-known law of Bob Denard, where you're scaling the device specifications and you're scaling the geometrical specifications in order to keep the power density constant. And you see on the top graph here that was working very nicely up to the early 1990s. And then only geometrical scaling was not doing anymore. You had to go over to implement a second scaling approach, and that one is called material and device scaling. That means you have to implement new materials. And here, for instance, on the top view graph, you see the drive current and the device performance versus the geometry. And you see in the dark blue area that only geometrical scaling is not bringing you to the right specifications. You have to do something with the material and with the technology. And here you see, only as an example, the impact, for instance, the green area of the high-K dielectrics and the red area of strain engineering. And most of us still remember the nice paper in 2007 by Intel dealing with the first commercial 45 nanometer transistor, where we had the high-K gate dielectric, we had the metal gate, and we were using silicon germanium in the source drain area in order to build in strain so that we got a higher mobility and a higher drive current. A third approach for scaling, we call that circuit scaling. That means you take dies with different functionality and you package them all together in one package. In that way, you're achieving a high functionality for the same silicon area. That's scaling, of course. And finally, there's a third approach of scaling. We call that architectural scaling. That means you're optimizing solutions. You're working at the system level. Now, we cannot do scaling without thinking about lithography. And depending on the time and the type of technology you're using, we have been applying for a long time 193 nanometer lithography. And we have then extended that by going over to immersion lithography. And then we have been using double patterning. And we have been using litho etching. We even went over to quadruple patterning. However, if you enter the area below 10 nanometer and you want to do cost-effective lithography, the only way to do that is by going over to extreme UV patterning. It's a huge investment to buy the machines, but you're gaining a lot on processing time and on the cost of your devices. This is only one example related to the masking steps that you need when you're going from 20 nanometer to 7 nanometer. And with the, I call it classical 193 immersion lithography and multiple lithography steps, you have to go from 20 masking steps, from 8 masking steps to 33 masking steps if you want to make 7 nanometer technology. If you use EUV lithography, then you can do it with 9 masking steps. So that means you're saving a lot of time in processing time, in cycle time, but also in processing cost. The second important material area is gate dielectrics. And we all know that if you're scaling the thickness of the well-known silicon dioxide below 5.4 nanometer, you're getting direct tunneling through the oxide, which implies that you get a higher gate leakage. The way out was to use materials with a higher dielectric constant. In that way, you can use a thicker gate dielectric without penalizing the switching speed. And there are a lot of materials that have been and are still investigated. However, and I got here a very nice view graph from Professor Iwai from Tokyo Institute of Technology. If you want to implement a new gate material, there are a lot of material parameters, process parameters, and phenomena that must be investigated and optimized. And I'm not going to discuss all of them. I'm only going to give you a little bit of flavor, but you have to control the defects in the high K layer. You have to control the quality of the interface between the high K layer and the silicon. You have to investigate whether or not you need interfacial layers or passivation layers. You have to look at the interface between the high K and the metal layer. You have to look at what is a problem of dipole formation. You have to look at the leakage current. You have to look at the reliability effects. You have to optimize the work function. That means if you work with high K, you have to switch over to the appropriate metallization system. So there are a lot of parameters that must be investigated and optimized before you can introduce a new high K material into a commercial device. And today we can say that the most common high K dielectric is an hafnium-based dielectric. Although at the research and development level, a lot of other high K materials are under investigation. Let's have a look at the evolution of silicon devices. And if we speak about silicon devices, we are starting, of course, with the planar devices. And then in order to improve in performance, we switch over to the FinFET, three-dimensional devices. And if you want to increase the drive current, you have to work with multiple fins. And from multiple fins, automatically, you go over to nanowires, can be horizontal or vertical nanowires. And from the nanowires, the next step is to go over to what we call stacked nanosheets, as you see very clearly in this figure. And here you see an example of nanosheets fabricated with a 5 nanometer technology. That's a TM micrograph from IBM. But that is not yet the end. You can go further because we want to do the ultimate scaling as long as we are not violating physics. And one next step that has been proposed by IMEC last year at IDM is called a fork sheet. Normally, if you have a FinFET, you have N channels and P channel devices. And the distance between the two type of devices is going to limit your scaling. So the same thing if you work with gate-all-around devices. But if you work what we call a fork sheet structure with a dielectric in between, you can minimize the distance that you need between the N and the P-type devices. And in that way, you can further optimize your scaling, you can go further in scaling down. So that means from FinFET, we are switching over to nanosheet, and finally to a forward sheet, where, as already mentioned, we have a reduced separation between N and P channel. We can better control the device variability by optimizing the work function. And in addition, we are getting improved performance because we have a reduction of the Miller capacitances. But also here there are limits. And a further approach, which is bringing us to the 3 and 2 nanometer range, is called complementary FET technology. Also, for the first time proposed by IMEC. And instead of putting the devices next to each other, you can put them on top of each other, either in an horizontal or in a vertical manner. That is what we call complementary FET technology. And here you see an example of such a device that was presented at the VLSI conference by IMEC only a couple of months ago in June. Here you see the PFETs, and here you see the NFETs. And you can see that the electrical performance is very good. And there was an invited presentation yesterday by Dr. Hiroshi from IMEC explaining more in detail the different fork structures and the complementary FET technology. And if you want to summarize the evolution on scaling the silicon devices, then I can use a view graph from IMEC, where starting from the 45 nanometer technology, think about Intel 2007, where you have a high K dielectric, a metal gate, and you have strain engineering. If you want to further optimize the device performance, because that's always one of the goals, to improve the device performance, you can go over to a 3D structure, a FinFET. Further optimization of the performance will lead to the implementation of so-called high mobility channels. That means instead of using silicon in the channel, you can work with silicon germanium, or even 3.5 materials. When you have put that to the limit, you can again play with the device architecture. You can go over to the nanowires and the nanosheets, or you can work with tunnel FETs. This low power consumption is very important. And I'm coming back to that in a moment. And then the next step will be again to play with the material. And nowadays there's a lot of research going on 2D materials. And then I'm not referring to graphite, but I'm referring to the huge amount of different other 2D materials that are being investigated. And there was also a nice presentation by Professor Lemmer. So that means normally you optimize materials, you change the device structures, again playing with the material, and you're recycling that a few times to come to the optimum scaling in order to cope with Moore's law. I mentioned tunnel FETs because what you want is a very high on current, a very low off current, and a very steep switching. And you can improve the switching speed by going from planar to FinFET to nanowires, and finally to what we call a tunnel FET. And the tunnel FET is nothing more than a PIN structure, where for a classical transistor, you got N in source and drain, or P in source and drain. Here you got a PIN structure. Because what you want to do is to minimize the subthreshold slope. And you can write down formulas for the subthreshold slope, taking into account the capacitances of the channel and the capacitances of the insulator. But the limit, the physical limit for the classical devices is 60 millivolt per decade for the subthreshold swing. You cannot go lower. If you want to go lower, then, for instance, you have to work with another operating principle. Instead of relying on thermionic emission, you can go over to tunneling. And with tunneling, you can go very, very low for the subthreshold swing. There are reports dealing with, for instance, a few millivolts per decade. Another way to come to a lower subthreshold swing is by trying to get this factor, 1 plus the ratio of the capacitance, smaller than 1, what is normally not feasible. However, there's a lot of reports available dealing with what is called negative capacitance FETs. And you can obtain negative capacitance by putting in series with the gate dielectric a ferroelectric material. And I know there is a lot of debate going on. If you go to the tier 1 conferences like VLSI, IDM, you see many presentations on so-called negative capacitance FETs. And there is a strong debate on whether we are dealing with a real negative capacitance or we are more dealing with what is called an instability. But it's quite important to know that those type of devices are investigated and are also giving very promising results. Only one slide to say that also in the memory devices, there is a strong evolution in order to optimize the performance. But we all know that for memory devices, there is a limit on the scaling. You cannot follow the normal scaling rules. That means here people are going to look at how to optimize the concept of the memory and how to optimize the material. That means you can work with spin, torque, transfer magnetic random access memories. You can have phase change memories. You can have resistive random access memory, conductive bridge random access memory, ferroelectric random access memories, and you can also have 3D NAND structures. And very recently, only 2 weeks ago, there was an announcement by Micron that they have a 176-layer NAND flash. So there are different approaches in order to optimize the type of memory device that you need. And optimizing means that you have to make a compromise between the access time and the density. And depending on your application, you will go for one or the other. So I'm not saying that one type of device is an overall winner. It's all depending on what are the requirements that you want for your memory. Now, in order to improve the drive current, I mentioned already that you can play with high mobility materials. Germanium is one possibility. However, if you work with germanium, there are 3 important challenges. The first one is that you want to have a high quality gate stack. And it's not obvious to put a high K material directly on germanium. You have to do something with the interface. And we call that passivation of the interface. And there are different approaches to do that. The second challenge is a contact technology. It is much more difficult to make good contacts on germanium than on silicon. And of course, the third one is integration on the silicon platform. You don't want to process on bulk germanium wafers. You want to process on silicon wafers on which you have germanium regions. But if you want to put germanium on silicon, you're going to deposit epitaxially 2 materials with a different lattice constant. That means there is lattice mismatch. And for silicon germanium, the mismatch is 4%. And mismatch means that you have defects. And you have to optimize your processing in order to minimize the defect generation. You cannot bring it to 0, but you have to minimize it so that you're not going to see the impact of your defects on your device performance. And one of the excellent devices that have been reported already in 2010 by Pilarazzetti from Intel was a germanium quantum well device. And I've included this view graph not to explain in detail how this device is working, but only to illustrate that it's not just putting germanium on silicon. In order to do that, you have to work with different types of buffer layers. And the reason for implementing all the buffer layers is to control the defect density. Over the last decade, germanium devices has been extensively investigated, and many types of devices have been reported. For instance, here you see an example of a planar transistor built on strained germanium deposited on silicon, but with a strain relaxed buffer layer. This is a device of 65 nanometer gate length with high K dielectric and metal gate. You can also use germanium to build FinFETs. Here, for instance, you see a germanium FinFET where, again, the germanium was grown on a silicon germanium buffer layer. But it's also feasible if you optimize your epitaxial processes to grow the germanium directly on the silicon to see that your defects are confined to the interface so that in the fin itself you have an extreme low defect density. You can also use germanium to make tunnel FETs. And in principle, you can make a germanium PIN structure. However, you don't want to do that. You want to have germanium in the source because you want to increase the tunnel probability, what is going to give you a higher drive current. But if you put also germanium in the drain, then you're going to get a higher leakage current. And of course, you want a very high on-off ratio for those type of devices. That's why a very promising approach is to use only germanium in the source of your tunnel FET. And germanium have also been used to fabricate, as you can see here, nanowires, where we have germanium nanowires with a thin silicon layer on top of it before depositing the high K dielectric. So we can say that very good, even promising performance of germanium devices has been reported, especially for P-type devices. However, if you want to have high-performing N-type devices, then you better switch over to 3.5 materials. But however, 3.5 materials is another problem. If you want to put, for instance, indium phosphide or indium gallium arsenide on silicon, you have a lattice mismatch of 8%. That's too much. That's going to give you a lot of defects. That's the reason why, for instance, you can first grow epitaxially a thin germanium layer, and on top of that, you can grow your 3.5 material. Because between germanium and indium gallium arsenide, the mismatch is only 4%. An elegant way to do that is relying on what is called using aspect ratio trapping for the epitaxial growth. That means you're starting with shallow trench isolation, where you got oxide and silicon areas. You're etching away the silicon, and then you're growing in those areas your germanium or your 3.5 material. As I mentioned, you have to be careful with defects. One type of defect is lying at the interface, the misfit dislocations. Another type of defect are the threading dislocations coming to the surface. The third type of defects are what we call the planar defects, like for instance, stacking fault. And that means you have to optimize your epitaxial process in order to control the defect generation. And one way is to rely, for instance, on the aspect ratio. Here you see defects in a 200 nanometer wide and a 100 nanometer wide trench. And you see that for the 100 nanometer wide trench, the defects are more located near the interface, meaning that you got a very nice defect-free region on top. So in order to do nano-rich engineering, as we call it, you have to rely on the aspect ratio. And here you see in this figure that the defect density is strongly decreasing as the trench width is decreasing. And in general, you can control the threading dislocations. They are not going to cause you a problem. It's more difficult to control the stacking fault. But the nano-rich engineering approach has been successfully used for germanium, gallium arsenide, indium gallium arsenide, and so on. Here you see an example of gallium arsenide on silicon, an example of gallium antimonide on gallium arsenide on silicon, and a final example where we have indium gallium arsenide on silicon. And on top we have an indium gallium phosphide capping layer. So at the recent conferences, very excellent performance has been reported. And here, for instance, you see an example of an indium gallium arsenide FinFET on 300 millimeter silicon wafers. This is a report by TSMC, where you see, and I'm not going to explain the details in view of the timing, but for a 120 nanometer device, they are very, very promising device performance parameters. Similar work has been done by IBM Samsung, where they have been using also indium gallium arsenide to make silicon FinFETs with 20 nanometer gate length, also again resulting in excellent device performances. Instead of FinFET, you can also use indium gallium arsenide for MOSFETs. As for instance here, an example of work done by IMEC, where you can even optimize the gate dielectric by using the appropriate interfacial layer and using a very thin layer of platinum silicon oxide. Very good performing indium gallium arsenide MOSFETs have been reported by IBM Zurich, where here you see the data relying on a 13 nanometer gate length. I must say that in this case, wafer bonding was used to get the indium gallium arsenide layer on top of the silicon, where in the other approach we were using epitaxial growth. And also the device performance is excellent because for a 13 nanometer device, they are achieving a drive current of 300 microamps per micron. This is a very interesting example. Is data from National University of Singapore in collaboration with MIT. And they did a monolithic integration of a gallium arsenide FET and a gallium arsenide, aluminum gallium arsenide laser. And that is very promising. If you can co-integrate lasers with standard FET device on a silicon substrate, I think that's opening a huge range of new applications. Nowadays, there's also a lot of interest in 3,5 nitrides. And here you see a comparison between the blue silicon, the brown silicon carbide, and silicon nitride, the green one. And you also have a table with the different data. I'm not explaining that again because of the timing, but with gallium nitride, you can achieve high voltages, high power, high efficiency, and very efficient light emission. So that means that is going to result in very, very promising device components. And if you look at the on-resistivity versus the breakdown voltage, there is a limit for silicon, there's a limit for gallium nitride, and there's a limit for silicon carbide. And the limit for gallium nitride is further away than for silicon carbide. And I know there is a strong debate going on between silicon carbide and silicon nitride, which of the two is the most promising material for future devices. Well, I would say depending on the final application, there is a market for each of them. However, today, the data reported for gallium nitride, as you can see, is very, very promising and is reaching further than the silicon limit, but not yet the limit for gallium nitride. So that means, notwithstanding the excellent data, there is still room for improvement. And this is a very nice view graph, because this is giving the gallium nitride power market evolution as a function of time. And we have different applications, the green or the consumer application, the blue or the telecom application. But if you go from 2020 to 2025, then the prediction is that within 5 years, there will be a 10 times growth in the use of gallium nitride. And that's why there are more and more companies now also starting manufacturing of gallium nitride devices. And also this month, there was a startup of a new gallium nitride facility in Texas by NXP. And if you look in the literature, you will find already different type of devices that have been fabricated using gallium nitride. In 2015, there was a gallium nitride nanowire. More recently, you see a very, very small area gallium nitride wire. You can make gallium nitride defects on gallium nitride. And of course, you can make gallium nitride nanowires on silicon. And that's what we are really looking at. We want to be able to produce gallium nitride devices, gallium nitride circuits on silicon, because then we can do processing on large area silicon wafers. But as already mentioned, in order to grow gallium nitride on silicon, you also need the appropriate buffer layers. That means you have to work again on defect control. And similar as for other 35 materials, you have to optimize the gate dielectric. You have to work with passivation layers in order to get a very good interface quality. And you have to work on the uniformity and the reproducibility. However, we can say that heteroepitaxy of gallium nitride on silicon is a very effective solution from a viewpoint of cost and performance. And if you want to make gallium nitride devices, there are different approaches. You can work with a MOSFET, where you have the standard gate dielectric. You can work with a high electromobility device. There you don't have a gate dielectric, but you have a depletion mode device. That means the device is normally on, and you have to apply a voltage to switch it off. However, you got high performance. Or you can do a combination of the two, depending how deep you're etching, whether you're stopping on the aluminum gallium nitride layer, or you're going deeper, and whether or not you're using a gate oxide. But you can make what we call a MOS-HEMT. This is still a depletion mode device, but got a high performance and a low gate leakage. And here you see a very nice TM picture of a MOS-HEMT. Quite recently, there was a report from Cornell University on the T-gate gallium nitride HEMT device on silicon. And I've included this view graph only to point out that if you look at the frequency performance, that means the oscillating frequency versus the cutoff frequency for different devices, but here the red data, or for the T-gate gallium nitride HEMTs, and you see that they were able to achieve an Fmax of more than 200 gigahertz and an FT of 250 gigahertz. This is very good frequency performance for gallium nitride on silicon. Can we compete with gallium nitride on silicon carbide? The answer for the moment is no, because therefore the best device reported for gallium nitride on silicon carbide is an FT and an Fmax of 450 gigahertz. However, if you look at the evolution, FT versus the gate length, and if you look at the blue data, that's for gallium nitride on silicon carbide, but if you look at the red data for gallium nitride on silicon, then you see that the frequency performance is coming closer to the one that we got for gallium nitride on silicon carbide. But there's still quite some research that has to be done. If you look in general at the frequency behavior of different technologies, then you can put together this benchmark. This is the oscillating frequency versus the cutoff frequency. For the black squares play the silicon devices, the blue squares for silicon FinFETs. And you see that you got a better frequency performance for the planar devices than for the FinFETs. However, if you want to increase the frequency performance, you can work with silicon germanium ABTs. You can go a step further. I've included here the gallium nitride silicon carbide, but as already mentioned, they are restricted to the 450 gigahertz for FT and Fmax. If you really want to go higher in Fmax, then the solution is to work on indium phosphide. And here you see some data of different authors on indium phosphide ABTs. And you see that we are entering the terahertz region. The best device reported so far that I could find is an indium phosphide high electromobility HEMT, where you got about 1.5 terahertz for Fmax and 750 gigahertz for the FT. So using indium phosphide is moving Fmax into the terahertz range. And then keeping in mind what I mentioned a moment ago, that you can finally work with indium phosphide on silicon, I think there is a very bright future for new type of high frequency devices. Finally, in the remaining couple of minutes, I want to say a few words on 3D sequential integration. What you want is to increase the package density. You want to get more functionality in a smaller silicon area. And one way is to put dies with different functionality in the same package. And this 2D packaging, we call that system in a package. However, you can also put layers with different functionality on top of each other, really coming to 3D functional partitioning. And one way to do that is, for instance, to work with dielectric wafer-to-wafer bonding. You have two different wafers with two different functionality, different type of processing. You do a room temperature wafer bonding. You do a temperature step to improve the bond strength. And then you're thinning the wafer, and then you're doing through silicon vias. And finally, you do the final packaging. Another approach is what is called the hybrid wafer-to-wafer bonding. Again, you start with two wafers with different functionality, but now in one wafer, you got already through silicon vias fabricated. Then you do again the room temperature wafer bonding, a temperature step to improve the bonding strength, wafer thinning, and then finalizing the packaging. So that means you can have to come to a higher functionality for the same area. You can use system in package. You can do wafer level bonding or die to wafer bonding. Both can be used. But there is also a third approach, which is called device level stacking. That means you are going over to three-dimensional integration. How is that working? Well, you have a bottom layer, let's say a silicon wafer, where you do the normal standard processing. Then you grow a layer on top of that. You do processing in the top layer, and then you do the final metallization. In that way, you get a higher contact pitch, higher contact density, and the alignment is done by lithography, not by bonding. That's give you the possibility to have different type of devices in the top layer and in the bottom layer. You can play with the gate oxide strain engineering, different type of channels, and you're gaining in the wiring length between the different transistors. But you have to be careful. If you do processing in the top layer, you have to control thermal budget. One example here is, for instance, the copper interconnects. If you go higher than 500 degrees centigrade, the interconnect is becoming very poor and you got voids. That's why people are looking, for instance, at tungsten or cobalt. And here you see, for instance, the performance of tungsten after a 1 hour anneal step at 650 degrees centigrade. Both tungsten and cobalt is performing much better than copper. In general, you have to be careful with temperature budget because you have to control the quality of the top and the bottom oxide. If the temperature is too high, you got a recrystallization of the bottom gate dielectric, but you don't want. You have to optimize the contacts in both type of defects. The layer transfer can be done with wafer bonding, or more elegant, to my opinion, by epitaxial growth. And you have to be careful with dopant activation. That means in the top layer, you can, for instance, implant your dopants, but if you do an implantation with the dopant, you need a temperature treatment for two reasons. One, to activate the dopants. Secondly, to anneal out the implantation defects. If you do that in silicon, you need high temperatures. Or you have to work with special techniques like, for instance, excimer laser annealing. That's a possibility. Another approach has been proposed by IMEC, where they are using a standard silicon wafer processing on one wafer. On the second wafer, there's a Y wafer. They already do the dopant implantation and annealing at high temperatures. Then you do a wafer bonding, and then they are fabricating the devices in the top layer, in which case they are using a cold process. And that's an example where you got at the bottom bulk FinFET, and at the top you got Johnson-less FinFET. But there are different combinations possible, as already mentioned. Here you see an example from Stanford, where they have put 4 different layers on top of each other. One silicon layer one layer for resistive memory devices, a second layer for resistive memory devices, and one layer for carbon nanotubes. And then they've been doing the first process, the silicon devices, using the standard high temperature processing, and then they've been using lower temperatures, lower than 200 degrees centigrade, to do the fabrication of the different type of devices. And finally, that's my last example, published very recently, was presented at the VLSI conference in June, is work coming from Intel, where using gallium nitride on silicon, because that's always the basis, starting with silicon. Processing gallium nitride on silicon, they have been making an enhancement mode gallium nitride transistor. Then they have used a second wafer and did wafer bonding. And then they have been processing silicon devices in the top layer. And in that way, you got very special type of devices, combination of gallium nitride device, where you can have high frequency, you can have high power, combined with silicon devices. And to my opinion, that's opening a totally new range of different applications. As a takeaway, I would like to say 5G is around the corner. Sorry, 5G is there already. 6G is around the corner. Advanced silicon devices, or germanium and 3.5, are extensively studied and are very, very promising. 3.5 materials on the silicon platform are entering the market. Then I'm referring to indium phosphide, indium gallium arsenide, gallium nitride. But the two main challenges are the defect control and the quality of the gate dielectrics. 3D sequential integration has a huge potential for cost-effective manufacturing of a system on chip. There, the main challenge, as I've been demonstrating, is the temperature processing of the top layers. And I want to say 2D materials are gaining a lot of importance, and I strongly believe in the near future breakthrough of 2D materials. And as already mentioned, I'm not referring to graphite, and I was not able to say anything, but they were very nice invited presentations. Devices for quantum computing and artificial intelligence are also becoming very, very important and will be having a dominating marketplace. In summary, I want to say Internet of Things, while it's very important, but we have seen only the tip of the iceberg, and much more devices and applications are going to come in the near future. I thank you.
Thank you, Professor Kaur, for this fantastic exposition. You've opened up the entire canvas. The scaling, geometry scaling, materials, device architectures, 3D integration, it has been quite amazing.
It's a lot of material in a short time.
I just want to let you know that there are 850 delegates listening to your talk.
Oh, that's excellent.
Phenomenal number, right?
That's very good.
Unfortunately, we do not have time for questions, and maybe they will contact you later in future.
Yes, they can always contact me, no problem. Okay, thank you
again. Thank you again for your time, and we will now move to the next talk in the evening session today. It's my pleasure again to introduce to you Professor Thomas Thundat, whom I have known for several years now. He is a innovation professor at the University Buffalo, SUNY Buffalo, New York. He is also Canada Excellence Research Chair Laureate Professor at the University of Alberta, Edmonton, Canada, and a distinguished professor at IIT Madras. He was a research group leader for Nanoscale Science and Devices Group and UT Battle Corporate Fellow of the Oak Ridge National Lab until 2010. He received his PhD in physics from SUNY Albany. He is the author of over 450 publications in refereed journals, 45 book chapters, and 45 patents. He is an elected fellow of the American Physical Society, Electrochemical Society, American Association for Advancement of Science, American Society for Mechanical Engineers, ASME, the SPIE, American Society of Biomedical and Biological Engineers, and the National Academy of Inventors. His research is currently focused on developing new concepts in nanomechanical sensing, energy conversion, electrical energy transmission using single wire, and novel concepts for charge separation and storage. Today, he has very uniquely titled his talk, Vadis MEMS Chemical Sensors. Over to you, Professor Thomas Thundat. You have to unmute, yeah.
How do I?
Yeah, you are fine now. You're absolutely fine.
How do I share my screen?
At the bottom of your display, there is a share option. After video option, there is a share option, share content.
Share, yeah.
Yeah. So when you click share, it will perhaps pop up several windows. You will have to click on PowerPoint.
PowerPoint.
I mean, the particular window that you want to share. Or you can also share the entire desktop.
Yeah, maybe you can open the your slide first and then share the screen. Yeah, then you go to share and then you will see several windows. Okay. So you will see several windows and just click on the PowerPoint window.
I don't see it.
When you hit share, a pop-up comes in with several windows. When you click on share.
Otherwise, you just share the screen.
Yeah, that's what I'm trying to do. Unfortunately, it goes someplace else. Firewall, privacy.
It's not that. So Thomas, when you switch the share one, so whatever the window is coming at the top, just click on that.
What I see is open preferences.
No, he's getting some other
Like,
issue, some firewall issue or some security
yeah,
issue.
some firewall issues.
What happened?
So one option is you can email your slides to Neeraj Khare and maybe he can open it.
Yeah.
Maybe, sorry to interrupt you, maybe there's a problem that there is a second screen connected to your computer. Very often you have a computer and a larger video screen connected to it, and then it's not working. Then you have to disconnect the other screen and only have your computer.
Oh, it's a big thing.
This is WebEx. Very embarrassing.
No, it's okay. So Professor Thomas, when you push the share screen, what do you see on your screen?
I see open system preference.
Open system preference.
Press that, it goes into Cisco WebEx, Cisco WebEx meetings, Zoom, Microsoft Teams.
No.
WebEx meeting, right? So I try that. It says that I have to quit now. Maybe I will quit and join again.
Yeah, that would be better. Yeah. Just quit it and join again. Yeah. Good. Now it's working. Yeah.
Really. My apologies for
No,
this
it's all right.
app.
Go ahead.
Not
Okay.
used to WebEx. And thank you very much for the introduction. I'm really sorry about this issues. So there is a big need for IoT, and previous speaker has pointed out that towards the end of his talk. So there are lots of applications that we need sensors. So if the IoT, if we want to make IoT practical, then we need all kinds of sensors that are miniature and that can be used to detect all kinds of things. Currently, IoT has only physical sensors, acceleration, velocity, force, so on. But unfortunately, there is nothing that we can use as chemical or biological sensors. This is a picture taken from Radislav's paper, and he also points out the fact that there are no chemical sensors that has the chemical selectivity, specificity, sensitivity, and so on. So I'm going to talk about MEMS sensors, how we can make MEMS sensors chemical sensors. MEMS, micro electromechanical systems, satisfy all the requirements for an ideal sensor. except a couple of them. And that's what we are going to address. And we can microfabricate the sensors. And there are lots of people in the audience who are experts in this area. And because of the microfabrication, we can make it very low cost for mass deployment. And if you look at for example, cantilever arrays, it can detect multiple physical parameters at this moment in time with a very high sensitivity. And we understand optical sensing, the optical sensors are out there, cameras and so on. Acoustic sensors are there. However, olfactory and tastes are still not well understood. And we don't really understand how it really works. It is still, an area of active research. So converting these MEMS sensors, which are physical sensors, into chemical or biological sensors require lots of work. So these are some of the sensors that we worked over the years, and made it into an integrated platform. This is even a smaller version of the same thing. This is a little chip. Anja Boysen made it in Denmark, and there are 32 different cantilevers, all piezo-resistive readout. So this complete, device, maybe few millimeter by few millimeters in size. So the way cantilevers work, the cantilevers and cantilever arrays, it can give you multiple signals. The frequency, amplitude, phase, Q factor, bending. And they're also excellent temperature sensors. It can have a sensitivity around 10 millikelvin at room temperature without any cooling using bimetallic effect. So adsorbed mass, we can detect just measuring the delta F, which is the shift in frequency with respect to the original frequency and the mass of the device. Mass of the device is mostly nanograms. You can even tune it to even smaller devices. The bending, so suppose you have a cantilever, little like miniature diving board. Most of the sizes, the sizes of these cantilevers are around, say, 100 microns. That's what we prefer, 100 to 200 microns. And 1 micron in thickness. And if we have a asymmetric adsorption of molecules, the surface tension of the surface, like a silicon, will change. Solids have surface tension. We call it surface energy or surface stress. And molecular adsorption always, involves energy minimization, surface free energy changes. So that changes a differential stress on the top and the bottom, and the cantilever, undergoes some kind of bending, and we can measure that very precisely using either piezo-resistive detection, or we can use optical beam diffraction. And that's what's shown here. Basically, surface stress and the bending are connected. Change in surface stress will result change in length, change in the bending. We can also measure the very small changes in temperature, and that's very important. And so if we have, say, two materials, like a bimetallic effect, E1 and E2 are the Young's modulus of the first and second material, and alpha is the coefficient of thermal expansion. So as long as you can measure the bending, you have the temperature, and you don't need any specific cooling. So that is very interesting idea. So no other sensor platform has this versatility, giving you multiple signals. And in addition, we can make them into arrays, and then detect all kinds of different potentially chemicals and so on. And you can have all the electronics actually integrated here. I will show you that in a bit. And you can also make it by mass production. This is a simple example of a multi-parameter detection. So let me explain. This PETN is a explosive that people used for shoe bomber used this for terrorist activities. So now you have a cantilever that is modified with some kind of a chemically selective agent on the surface, like a self-assembled monolayer, or for example, or polymer or something. And when this molecule, so PETN, comes in and absorbs on the surface, it changes the free energy. And this is the bending is shown here, and as a function of time. This is the point of injection of the PETN without changing the flow rate. So that you can see that cantilever bent. Look at only at the red curve, and when you turn it off, it comes back to normal in the equilibrium position. And these blue dots that you're seeing are the resonance frequency of the cantilever, measured every few seconds and averaged it over and using a Lorentzian fit. So that basically follows the bending, the curve almost in a faithful fashion, and the scatter is because of the averaging involved. And so these blue dots, we can actually calculate the mass using the resonance frequency. So resonance frequency and the bending are happening at the same time, and the frequency, remember that we are not exciting it, is the natural Brownian motion or thermal motion of the cantilever. And the bending related to absorption energy. So if we manipulate these two quantities, you can actually calculate the absorption energy involved, and that basically says that it is a basically it said we have the hydrogen bonding. So this is another example. You have two cantilevers, or actually multiple cantilevers, and then you can have, say, biological receptors like antibodies and things like that. You can. This is looking for exosome, which are vesicles that can be used as markers for cancer, and you can detect multiple cantilevers at the same time, and which are coated with a different type of peptide, and then or antibodies, and they bind to this exosome. And so this is a completely packaged device. This is done at Oak Ridge, to implant in animals. So this is there are 8 piezoresistive cantilevers underneath this frit, so the vapor can go in. We were looking for blood gases actually. And all the electronics, including 8-channel telemetry, is included here. And it works with, if you open it up, there are 2 clips. You can put 2 hearing aid batteries, and then it works. So it can transmit 8 different data, and one can be used as a reference. So you can actually detect maybe 7 different chemicals. So this is what is implanted in a rat. You can see the rat sitting here. Basically, we cut this rat open and put this little device, which is actually very small, and give alcohol to the rat, and then rat will the sensor will transmit the data, and this is picked up by this antenna here and show real-time blood gases. So that was the idea, but we didn't continue this very much because of one big problem with the batteries. Battery life turned out to be a major problem. So this will be a problem in the Internet of Things too. So I will address that in towards the end of this talk, actually. I have a couple of slides. So let's look at the, we want to detect, chemicals in a complex environment. So one thing we can do is to, this is the chip. So we have modified these cantilevers with the different polymers and self-assembled monolayers. So they respond to a mixture of gas or something in a different fashion. Then you can use this electronic nose approach, or this nowadays what you call the machine learning. So we initially used but a PCA, and artificial neural net figure out what the chemical is. So initially you have to train. So I am showing only 4 cantilevers. There are coated with the different chemicals for absorbing, say, for example, acetone. When you send acetone, it has these cantilevers have specific pattern. 4 of them act differently. They have a rise time, they have a maximum height, their decay time, and so on. This is ethanol, water, TNT, toluene, unknown vapor. So then we can actually go and find out. Once you train it, you can go and find out the unknown vapor, how it detect. So, however, we ran into some problems with this approach. First, lack of chemical selectivity. And second one is a lack of reproducibility. And the third one was real-time detection, because the lack of chemical selectivity, that's what I am going to address in this talk. So if you have molecules in air, say parts per centimeter cube, parts per million, parts per billion, parts per trillion, and depending on the interaction between this adsorbed molecule and the surface, which we may modify it, or it can be gold or platinum or some kind of material or silicon. Depending on the interaction energy, so delta H, the heat of adsorption, you can have a monolayer of material. So there is a big concentrating effect by the surface. Now this is in concentration in centimeter per centimeter square. So another issue is the reproducibility, which I will come again in a little later time. And third one was the real-time problem, because the cantilever itself is extremely small. So the passive nano sensors and nano devices will have trouble with the real-time detection, because if your molecules are coming by diffusion, it is going to take a long time to reach the surface. So now let's talk about this chemical sensing. Chemical sensing is nothing but a chemical interaction. Chemical interaction like a delta H, heat of adsorption. The molecules have to adsorb on the surface. And if you want the molecule to be, the sensor to be, reusable, it has to regenerate. That means we need the interaction energy equal to KT. Kb is the Boltzmann constant, T is the temperature. So the ambient temperature, that will give you an energy of 4.14 times 10 to the power minus 21 joules. So that is the hydrogen bonding. So we basically use hydrogen bonding or van der Waals interaction. Unfortunately, there are so many molecules that can bind with the same van der Waals interaction or hydrogen bonding. What do you call the physisorption? It won't reverse. So we have to play between these two things. It's extremely active, but at a cost, the cost of irreversibility. So then we realized that these dogs, they may not be detecting, for example, explosive. They don't detect explosives because most explosives have very low vapor pressure. So dogs are basically detecting a bouquet of volatile organic compounds with high vapor pressure. So for example, TNT, it has toluene, acetone, limonene, and breakdown product like DNT. So the dogs basically look at the profile of these responses because they have lots of cilia in their nose. So we can actually use this approach to detect, for example, differentiate between the different type of coffee, for example, wine, beer, Pepsi, and Coke. It can tell you the difference, but it cannot tell you what are the molecular constituents that is in that vapor order, for example. So if you want to detect just an order, this sensor is ready at this moment in time. But we would like to know the molecular fingerprints of this thing, and that is at present not possible. So you can use a pattern recognition. So people have been trying to do this. Is a paper, the recent paper. They have been trying to use PCA and machine learning we can actually define all kinds of variation in the signal process. And of course, you can actually get some kind of separation into different molecular groups depending on their functionality. So this work is going on. So as the more and more advanced versions of machine learning comes around, we can use very fine details that is available through this sensor array. We can use it for discrimination. So this is an excellent example. For example, if you look at the mercury vapor detection using, as a gold-coated silicon cantilever, you can see that we can also measure the resistance of the cantilever. The gold film has a resistance of a couple of ohms, and when the mercury absorbs on it, it also changes the resistance. You can measure that resistance, that is shown here on this axis, and here is the cantilever bending. And these are different concentrations of mercury vapor in a parts per billion level. And you can see that the resistance variation is much faster than the bending. So that gives you another information that can be used in pattern recognition concept. These signals, resistance variation and bending, are orthogonal signals. So they are linearly independent. But you can plot the bending versus the resistance change. And you can see that they follow pretty well together. Of course, the resistance variation is actually faster compared to that of the bending. So now coming back to the chemical sensing idea, you can say that the biosensors are extremely selective, and if that's why antibody antigen and so on, people are using it. And in biomolecule, there are lots of binding site. The antibody antigen works with multiple bonding, like hydrogen bonding, electrostatic interactions, and hydrophobic, hydrophilic. So all kinds of different interactions are there. So selectivity is e to the power minus e to the delta G by KT, and delta G is the Gibbs free energy change per interaction. If there are n interaction, so you have the selectivity, very high selectivity. But most of the things that we make, synthetic polymers or self-assembled monolayers, they have only one binding site. So that is not very selective. So we cannot use that, we cannot follow nature. Nature uses a multiple binding site. We don't have that. So following the nature blindly, like the fall of Icarus, it will be a bad idea in this case. We have to think something different, because biology and biological systems are more complex. So the idea of molecule detect molecule is borrowed from biology, and that's why we call it receptors and things like that. So that concept, present day, currently that we are using in chemistry, may not be the best way to detect molecules with a high specificity or high selectivity. So this is a quote from Einstein. Einstein says that problems cannot be solved at the same level of awareness that created the problem in the first place. That means today's technology cannot solve today's problem. That means we have to think something different. So now let's think about selectivity without receptors. Can we think like that? Most of the current miniature sensors don't use this phenomena. So we can actually use this multi-physics approach. Suppose this is a sensor, you have input of molecules, and some kind of a signal comes out. That's what we call the primary response. Say frequency change, bending change, resistance change, things like that can happen, and it gives you some output that we can actually use some kind of machine learning and kind of separate it, but we cannot separate it too much when the concentration of the molecules are extremely small. Ultra trace detection is extremely difficult. If you have lots of molecules, of course, you can separate it out because it, in a pattern recognition, it will move away from the origin, right? So now we can look at the secondary response. And for example, you send the molecules in with the sensor, and if we can modulate the properties of the molecule without not looking at the chemical interaction, but we look at the properties of the molecule that are already absorbed, then that will give you an orthogonal signal or many orthogonal signals that can be used as an output. What are this modulation technique? We can use optomechanical effect. We can, for example, infrared, near, and or mid-infrared. You can use optical too, or thermal. We can use a differential scanning calorimetry type approach where you can heat the cantilever by passing current through the cantilever and then dissolve the molecule at certain point in time, certain temperature. Molecules will dissolve, and you can actually get some kind of a discrimination. And another one is electrochemical. You can use a magnetic, or you can have a different combination of this thing and look at the tertiary signal if you prefer. So this is the way. Let's look at this infrared interaction with MEMS devices. Remember, MEMS devices have extremely low thermal mass. That means if one photon is absorbed, there is enough energy that will change the temperature of the cantilever very much, because specific heat and the mass is very small. The thermal mass is extremely small. So the beauty of the approach is that using low thermal mass, we can get some kind of a discrimination. For example, infrared, this is around mid-infrared region. They like water molecules, SO2, CH4. They are basically, you can discriminate them by exciting that bonds. So when the molecules are excited, it has two different pathways, radiative pathways, which are mostly towards the atoms, for example. For molecules, there is always non-radiative path. So radiative path and non-radiative path actually occur for big molecules. So we can actually use, and in the vibrational spectrum, the density of states are so close together, so they have to ring down through all these things. So every time it comes down, this continuous state, they are losing energy, and that becomes heat. That is the radiative path. And you can use this mid-infrared region for environmental monitoring, defense security application, medical diagnostics. So it depends on what wavelength we can excite the molecules with. So basically, the way it works, we have a glow bar, which is a very small device, and a filter wheel, that will select the wavelength. We basically focused on the cantilever. And in this case, cantilever bending is monitored with a laser diode and a position sensitive detector. And this is a TNT spectrum. So this is, remember, this is a cantilever bending as a function of wavelength that we are exposing the cantilever to. And the TNT is absorbed on the cantilever. Remember, this cantilever is a bimetallic cantilever. And TNT absorbed on the cantilever by physisorption. There is no chemical interaction. There is no polymer. There is no self-assembled monolayer. TNT molecules are sitting on the surface by van der Waals interaction, basically. So when you shine the different wavelength, these molecules are going to get excited. The bonds are going to get excited, and that is what we are seeing here. The 6.5 and 7.5 micron peaks that you see are are due to asymmetric and symmetric stretching of CNO2 bonds, basically. And this is the PETN. Again, you can see identify these different peaks, and they are very unique to PETN. So if I see this thing, I can actually say that that's PETN and TNT like this. And remember that these are physisorbed from vapor, so there are maybe picogram amount of material adsorbed on it. And now you can expose it to mixtures of both TNT and PETN and do the exposure to infrared, different wavelength. And what you see is a linear combination of this curve and this curve together. So now we can start increasing more and more vapors, and then we can start analyzing the data. And this is where the machine learning and AI technique will come in handy, because if you have lots of molecules, you are going to get a forest of peaks. But we know these peaks are so unique, they don't change if you mix them together. So it is much easier to discriminate. So this is a naphtha, which is like a kerosene. So this is the cantilever data. Remember that we are using a glow bar, and this is the ATR, attenuated total internal reflection, or FTIR. These peaks are beautiful, but because they have lots of material, milligrams amount of material, and a very powerful light source, very clean light source. And here we are using a glow bar and with an aperture. So aperture will let in too many wavelengths at the same time. That's why we are not clearly discriminating all these peaks. If we were to use a laser, for example, we should be able to see it much resolved images. Sorry about this circles, it's all got messed up in the it basically show that they follow each other very well. And we can actually identify these different bonds because these are all available in the database, in the NIST database. So all this bond vibrational spectrum, we can actually identify them just looking at the different peaks. This is another one of pain, and again, we can also see that. Remember that this is a cantilever bending. This is a non-radiative decay. We don't use Beer-Lambert's principle here. It is just heat. And this is the complementary one. We are the FTIR basically uses the photons and Beer-Lambert's principle. So these are complementary signals. So that's why you see the peaks are occurring at the same location in energy, but the amplitudes are different. And you can even detect methane. Methane, for example, CH4 is totally inert. It doesn't even absorb on surfaces, but they have some residence time because they have some absorption energy, and that is around nanoseconds. So they may stay on the surface for a nanosecond. And if you are exposing to, say, 1% volume percentage of methane, so at any moment in time, there are some molecules out there, they are absorbing and desorbing, and that we can see the spectrum. And then we found that is around 18 femtogram of methane adsorbed, and that is giving out the signal, actually. We can also make the thermal mass even smaller. then you lose the resonance frequency because it will get a little harder to measure the resonance frequency without much complex equipment. So this is a nanowire, and you can actually do the same thing, expose it to different wavelength. And this, in this case, the RDX is absorbed on the cantilever, and the red is there's a nanowire data, and the blue one is a FTIR image spectrum. And you can see that the spectrum of the nanowires are much sharper compared to FTIR, because as we make the device thinner and thinner and smaller, lower thermal mass, the response time is faster, and you can see the resolution in time get much better. That's what is shown here. And so people have asked me, oh, what about, for example, liquids? Can we do this in liquid? Again, we have a cantilever, and we can have a microfluidic channel developed on it. These are the pictures showing the hollow channel on the top of the cantilever, and so you can. It's around 50 picoliters or so, and you can actually get the spectrum. For example, this is the cantilever, the channel. You can measure the density of the liquid by vibrating it in time, and since the volume is known, you can calculate the density from the resonance frequency change. You can look at the viscosity. If you look at the Q factor, you can find out the viscosity from it, or you can light and get the spectrum like the one I showed you earlier, or thermal properties, shine a powerful laser, and how the heat is being absorbed, and and the decay curve. So all this information, so cantilever actually can give you multiple information for biosensing as well as the chemical sensing. This is the glucose and fumarate inside the channel, and this is the cantilever bending, and this is the wave number, and they match pretty well, actually. And you can also do electrochemistry if you want. I mean, this is the current versus voltage, with respect to a silver reference electrode, or actually quasi reference electrode. So you can see that this is the Gibbs-Duhem equation. You can actually ignore some of these parts. Basically, you don't need all the full all Gibbs-Duhem equation. Basically, it's showing that the current versus voltage. This is a cantilever as the electrode, and for different concentration, you can see this is a ferrocene methanol, the reduction oxidation peak, and you can also measure the bending at the same time, and then they don't change with the concentration. It looks same. And it gives you some more information that all the interactions are happening at the very interface. That's why it doesn't change. The bending doesn't change with concentration. And so another problem I talked about was reproducibility issues. We make a cantilever, say 100 cantilevers, self-assembled monolayer, uniformly put it on the surface in the lab conditions. But when you look at the response, there is a big distribution in the response for the same analyte, same concentration, for 100 identically prepared cantilever devices. The reason is that if you look at the gold, for example, deposited on the surface, it has grains and things like that. On the top of that, it's patchy. That means it is not uniform. So we found out that as long as if there are vectorially connected, that means if the modification is like this, there is no change in bending. But if there are, if we make it only towards the end, you can see that it bent a lot. And if it is very towards the end, it doesn't happen. So I think I'm running out of time. So I will basically go a little faster. So this is what a molecular recognition at this time looks like. Everything is coming together, and all these different parts that people have been working on it, and so we will have more and more a better idea about the how to address this challenge. So one more thing, we talked about the battery here. That's why we stopped this research, because we want to get out of the battery. So this, we say that we can actually address this battery challenge. We don't need two wires. Thus, of course, electrical engineers and physicists may find it harder to believe. You don't need a return path, even ground. You can have a single wire. We can set up a standing wave. It's a quarter standing wave, and get the device work. So this is these are rubber buckets, wooden stick, and one wire and light bulb, and a little metal piece to reflect the wave back. So this length is λ/4. So we have changed the frequency to higher frequency. So this is an example. This is a wooden desk again. This is a single wire comes in, and this is a 50-watt light bulb. Remember that current and voltage are out of phase here because it's a standing wave, so it's very safe. So he's touching it, and it comes on, right? So let's go to the next one. And it has a high efficiency. So this is a two little device, robotic devices you can buy from Walmart, and they have batteries taken out of it, and they touch by their leg on this aluminum foil. Aluminum foil has the power, so they can walk around, and on the top of that, we can also communicate with them, and they can also communicate with us without using electromagnetic waves. So that makes life much easier. This is an example where the rotating joints can also be used. This is a little motor. There's a one wire comes in here, and there's a two LEDs, and there's a stick. So this is a little coil that converts into high frequency. You can see that it also came on. It's also vibrating. So we can actually apply this idea, actually rotating machines and things like that. So that means we can actually implant the sensors in the people and use a watch, for example, as a power source, centralized, and you can power this whole body. That's what's shown by person here. He connected it to his hand, power comes on his hand, and he also have done the graph. So there is a hole drill in Tennessee, and we are powering the whole ground, and we have lots of sensors. I don't have the time to go through this. So we can also power the ground for our agricultural sensors. So let me stop here. So this is the summary. MEMS, imagination is more important, and if you can imagine it, you can make it, like a Feynman said. And the Cantilever platform has all kinds of things that we can use to use our imagination. I'll stop here. Let me, how do I get out?
Thank you very much, Thomas, for a great talk on sensors, and particularly cantilever-based sensors and different sensing modalities and applications to IoT and a variety of areas. Again, we do not have time for questions, and on behalf of the organizing committee, my sincere thanks to you for sparing your time. Thank you again, and over to you, Professor Neeraj Khare.
Yeah, thank you very much, Professor Naukant, for conducting this session very well in time. I just express my thanks to Professor Thomas and Professor Claeys for accepting our invitation for this evening talk. Thanks a lot to you, and thanks to Naukant for chairing this session. Thank you very much. Good evening. Bye.
Thanks.
So as I informed you that this has been watched by 870 delegates, this your talk. And apart from that, we have also streamed it to IIT YouTube, and I'm sure that many people must have watched it. Thanks a lot for your.
Okay, bye.
Bye. Bye.
Bye.
Bye. Leave the meeting. Should I leave the meeting?